taking some pretty complex scientific concepts and breaking them down so you can see exactly how the future is being built. We are looking at a fascinating process that honestly sounds a bit like culinary arts, but is actually cutting-edge chemistry. Think of it like a master recipe, but instead of, baking a cake, we're creating next-generation materials that power our tech, clean our water, and even advance medicine. We are talking about the hydrothermal method. So here's the massive question for you. How do we actually build a future, literally one molecule at a time? When scientists and engineers need to create materials with incredibly specific properties, stuff that's highly pure, perfectly shaped, and structurally flawless at a microscopic level, they can't just carve it out of a block of rock. They have to grow it. And to do that, they use what is essentially a high-tech pressure cooker to solve some incredibly complex chemical engineering problems. Okay, let's dive right into this. Here is our roadmap for today. First, a quick welcome to the nanoworld. Second, we'll walk through the 6-step hydrothermal recipe. Third, controlling the chemical chaos. Fourth, the shapes of the nanoscale. Fifth, why this method wins out over others. And finally, we'll look at how this is powering our future.
All right, kicking things off with Section 1, welcome to the nanoworld, and the basics of hydrothermal synthesis. The hydrothermal method is an absolutely powerful wet chemical process. At its heart, it's a fairly straightforward equation. You take an aqueous solution, add heat, add pressure, and boom, you get nanomaterials. Essentially, scientists run chemical reactions in water inside a heavily sealed container called an autoclave. They crank the temperature up, usually anywhere from 80 to 300 degrees Celsius, and because it's a completely sealed environment, as that liquid heats up, it creates its own immense pressure. We call that autogenous pressure. This very specific, intense environment allows us to form well-crystallized nanomaterials with unique shapes that are just notoriously difficult, if not impossible, to get any other way. Let's move on to Section 2, the 6-step hydrothermal recipe and what actually happens inside that autoclave. Think of this as the ultimate 6-step baking process. Step 1, you've got your precursor solution. This is where metal salts and other chemicals are dissolved in deionized water to form a perfectly mixed solution. Step 2, this solution gets carefully transferred into the autoclave. But this isn't just any container. It's a stainless steel vessel lined with Teflon, which prevents any unwanted reactions with the metal walls. Step 3 is sealing. It has to be bolted down incredibly tightly to withstand the extreme environment it's about to endure. Step 4 is the heating phase. The whole unit goes into an oven and is heated to that target 80 to 300 degrees Celsius for a very specific amount of time. Step 5 is absolutely crucial, cooling. You have to let it cool down naturally to room temperature. You definitely don't want to shock those newly formed crystals. And finally, Step 6 is recovery. The new product is collected, washed several times to strip away any leftover chemicals, and then dried out to reveal the final nanomaterials. Now, to avoid just ending up with a lump of useless sludge at the end of all this, we turn to Section 3, controlling the chemical chaos, and the key dials scientists use. What's really fascinating here is how tweaking just 6 specific parameters can completely alter the final product. It's a highly tuned symphony of variables. Temperature, for instance, heavily dictates the crystal phase, the size, and the ultimate shape of the material. Then you have pressure, specifically that autogenous pressure we talked about, which boosts the solubility of the chemicals and actually speeds up the reaction rate. The pH of the solution acts as a master control for how the particles nucleate and grow. Reaction time determines the final crystallinity. Leave it cooking longer and your crystals usually grow larger and more defined. The concentration of your starting chemicals controls how fast those crystals start forming in the first place. And lastly, stirring. Keeping the whole mixture moving ensures uniformity and gives scientists pinpoint control over the final structure. Which brings us nicely to Section 4, shapes of the nanoscale, or as I like to think of it, organic geometry. This is where you really see the magic of what happens inside that pressure cooker. You might expect an intense industrial chemical process to spit out jagged, chaotic lumps of metal. But instead, the hydrothermal method yields these pristine, almost architectural structures. We're talking sharp nanorods, completely smooth nanoparticles, long, delicate nanowires, and perfectly flat nanosheets. We even get these complex 3D structures brilliantly named nanoflowers, sitting right next to sharp, geometric nanocubes. It's such a striking contrast, right? A high-pressure chemical reaction creating things that look like they belong in a modern art museum or a botanical garden. And the best part is, this method is definitely not a one-trick pony. The hydrothermal process is incredibly versatile and widely applicable for synthesizing a massive variety of critical nanomaterials. We are looking at industrial heavy hitters like zinc oxide, titanium dioxide, iron oxide, and copper oxide. It's used for tungsten trioxide, tin dioxide, nickel hydroxide, and bismuth vanidates. The sheer range here is astounding, making it a go-to for complex oxides, hydroxides, sulfides, and phosphates. So why choose this over older techniques? That's Section 5, why this method wins and its key advantages. The crucial takeaway here is the stark contrast between this modern wet chemical approach and traditional solid-state methods. Solid-state methods are dry processes, and they often require violently high temperatures, sometimes well over 1,000 degrees Celsius, just to force the materials to react. The hydrothermal method uses water. Because the pressure inside that sealed autoclave enhances the reaction, the actual temperatures can be kept relatively low, between 80 and 300 degrees. That is a massive reduction in required heat, making this a far more energy-efficient and environmentally friendly approach.
And honestly, that lower energy footprint is just the beginning. The advantages are huge. It produces highly crystalline materials with incredible purity. We're talking very few impurities making it into the final product. Because of those 6 dials we discussed, it offers exceptional control over size and shape. Plus, it's scalable and reproducible. If you crack the recipe in a tiny lab, you can scale the whole shebang up for mass manufacturing. But perhaps most impressively, this unique pressurized environment allows us to synthesize new, metastable phases and complex structures that you literally cannot create using those older, traditional dry methods.
Let's zoom out to the macro level now for Section 6, powering our future and the real-world applications.
So how does this actually impact us? Well, the global impact of these tiny materials is staggering. In energy storage, the nanoparticles and nanosheets cooked up this way are exactly what make next-generation batteries and supercapacitors so incredibly efficient. For the environment, these materials act as powerful catalysts for water treatment, helping to actively break down pollutants. Over in the tech sector, the precision of those nanocubes and nanowires makes highly sensitive gas sensors, advanced fuel cells, and complex electrochemical devices a reality. And crucially, in the medical field, the high purity and biocompatibility of these structures are opening up revolutionary biomedical applications. There's a quote from the source material that really stands out as the ultimate summary of all this. It calls the hydrothermal method a green and efficient route for next-generation nanomaterials. By utilizing water, the most abundant and benign solvent on our planet, combined with just moderate heat and self-generating pressure, scientists have found a way to bypass a lot of toxic chemicals and massive energy waste. It is just a beautifully elegant solution to the historically messy problem of advanced chemical manufacturing. From the battery powering your electric vehicle, to the sensors inside your smartwatch, to the systems purifying the very water you drink, the nano world directly dictates our macro world. So, I want to leave you with this thought. How will the nanomaterials currently brewing in these high-tech pressure cookers shape your life in the next decade? It's pretty incredible to think about, isn't it? Thank you so much for hanging out, diving into this explainer, and exploring the foundations of our future with me. Keep learning, keep questioning, and I'll see you next time.